All right, so the ideal gas law for gases. Yes, it's a combination of all the previous gas laws. So it takes Boyle's law, Charles' law, Gay-Lussac, Avogadro's, all those equations, and combines into one big ideal gas law equation. That equation is PV equals nRT. All right, so pressure for the P is for pressure. Pressure must be in atmospheres or kPAs. Okay, not millimeters mercury, not torr, not PSIs or whatever. Has to be in those two. Volume must be in liters. Okay, not milliliters. Moles, that's what N represents. Temperature, as always, must be in kelvins. That's no apostrophe there, just kelvins. Now the R. R is the gas constant. It's called the ideal gas law constant. You have two values for ideal gas law constant. First one is 0.08206 liters times atmospheres over kelvins times moles. The other option for the gas constant, 8.31 liters times kPa divided by Kelvin moles. And now, if you notice between the two, you kind of wonder, okay, which one should I use? If you look, you'll see kPAs, and here you have atmospheres. So if your pressure is in kPAs, use 8.31. If your pressure is in atmospheres, use 0.08206. If it's in millimeters mercury or torr, convert it to either atmospheres or kPAs, whichever one you want to do. So that's the equation. So they're going to try an example. So we'll do an easy one first. You're going to find the volume of a 2.50 mole sample of a gas that has a pressure of 0.988 atmospheres and a temperature of 22.7 degrees. All right, so use our equation, PV equals nRT. So we have the pressure, 0.988 atmospheres. Find the volume. So that's going to be, say, V or X or whatever you want. N is for moles, 2.50 moles. R, so what's R going to be? Now you have atmospheres here. So we're going to use, go back to our constants here. So there we go. 0.08206 liters atmospheres divided by Kelvin moles. So that's going to go here. 0.08206 liters atmospheres Kelvin moles. And the temperature. All right, temperature is 22.7 degrees Celsius, but we don't want that. We're going to add 273 to it. So that gives us 295.7 Kelvin. All right, now, before you start doing all your calculations, let's make sure the units cancel out. All right, all the units in your equation should cancel out with the units in your constant. So here's pressures and atmospheres. That cancels with that atmospheres. Moles and moles. So those moles are gone. Those moles are gone. Kelvin and Kelvin. All right, so liters are the one unit you have left over. That's what you want here. All right, so now you do all your calculations here. Give V by itself, volume by itself. 61.4, that's your number. And again, liters is the only unit left over. There you go, 61.4 liters. All right, and that's how ideal gas law works. All right, another example. How many grams of ammonia, which is NH3, subscripts didn't work there. Fill a 14.5 liter container at that pressure and that temperature. All right, so PV and RT. All right, so do we have our pressure? Yeah, 99.7 kPa. We have our volume. Yep, 14.5 liters. N, okay, well it says how many grams. So in order to get grams, we need to find the moles first. So N moles, that's going to be our unknown. All right, so look back in your notes. What's the constant we're going to use? Yeah, we got to use, in this case, we have Kp as our pressure. So we're going to use 8.31 liters times kPa over Kelvin moles. All right, so different pressure units, so we got to use different gas constant. Temperature, so 165 plus 273 is 438 Kelvin. Make sure all units cancel out. kPa, kPa, liter and liter, Kelvin and Kelvin. All right, so moles is left over. That's the unit we want in moles. All right, so do your calculation. Stick in a calculator. You get 0.397 moles of NH3. All right, but now we want grams. So that means we have to take the moles and convert to grams. Remember to do that, you have to add up the molar mass. So if you look in your periodic table, nitrogen's molar mass is 14.01. Hydrogen's molar mass is 1.01, and you got 3 of them. All right, so 14.01 and 3 hydrogens, you add those up. 17.04 grams, that's what you want, that's on top. And 1 mole on the bottom. Moles cancel out. So 0.397 times 1704, 6.77 grams of NH3. All right, there you go. So 14.5 liters, that's big. So think of that, those 2-liter bottles of a soda pop you drink. So you got 2-liter bottles, you need 7 of those. So something about that size, only 6.77 grams. Really tiny amount. All right, yeah, so that just shows you that big volume only contains a little amount of gas. And that's because gas doesn't have that big of a density. All right, next video we'll talk about density.